As we've seen, having a basis for Rn consisting of eigenvectors of a matrix can be a very useful computational tool that allows us to avoid doing potentially time-intensive matrix multiplications. This is especially useful if we are interested in computing the powers of a matrix. So let's start off with a diagonal matrix. Our matrix D has entries lambda 1 through lambda n along the diagonal. If we wanted to compute the square of this matrix, then it's not hard to see that D squared is D lambda 1 E1, D lambda 2 E2, down to D lambda n En. We can pull the scalars through and then use the fact that D times EI is lambda I EI. So of course we're left with lambda 1 squared E1, lambda 2 squared E2, down to lambda n squared En, which simply means that if we square a diagonal matrix, we're simply squaring the entries along the diagonal. So proceeding in the exact same fashion, we can see that for any positive integer m, d raised to the m power is going to be lambda 1 raised to the m power times e1, lambda 2 raised to the m power e2, all the way down to lambda n raised to the m power en, which of course is just the diagonal matrix with lambda 1 to the m, lambda 2 to the m, down to lambda n to the m along the diagonal. So what's more, if each of the entries along the diagonal of our matrix is non-zero, then it's easy to invert our matrix. So we simply write 1 over lambda 1, 1 over lambda 2, 1 over lambda n along the diagonal, which we can think of course, as being lambda 1 to the minus 1 power, lambda 2 to the minus 1 power, down to lambda n to the minus 1 power. You can check that if you multiply d and d inverse, you will get lambda 1 inverse, lambda 2 inverse, all the way down to lambda n inverse along the diagonal, which is of course 1. And the same thing happens if you multiply in the opposite order. So of course, as long as our matrix has non-zero entries, then we can actually relax the condition that our integer m is positive from above. If lambda 1 through lambda n are all non-zero, then for not only positive integers, but any integer, so negative integers included, d raised to the m power is lambda 1 to the m e1, lambda 2 to the m e2, all the way down to lambda n to the m en. So of course, if we do not impose this condition, then we must enforce that m is a positive number. And of course, we should note here that because each of the lambdas are non-zero in this case, d to the 0 is simply the identity matrix. If we are able to diagonalize our matrix A, then we can find a similar formula for powers of A. So if we assume that A is similar to a diagonal matrix D, that is, it can be expressed as A equals P D P inverse, then A squared, which is simply A times A, can be written as P D P inverse multiplied by P D P inverse. Of course, we can reassociate. The P inverse and the P will cancel, so we'll get P D D P inverse, which is simply P D squared P inverse. So of course you could check that A cubed is going to give you A times A squared. So we can replace A squared with PD squared P inverse and A with PDP inverse. We can play the same association game, cancel the p's, and we'll see that we're left with P d cubed P inverse. Of course, if we continue in this way, if we take our favorite positive integer m, then a raised to the mth power will be a times a raised to the m minus 1 power. We can replace a with p dp inverse, and we can replace a to the m minus 1 with p times d to the m minus 1 power times p inverse. And of course, just like going from the case where we computed a squared to a cubed, we cancel the p's, combine the d's, and we get p d to the m p inverse. So here we see that if our matrix is diagonalizable, then it's almost as easy to compute powers of m as it is to compute powers of d. So if the eigenvalues of a are all non-zero, then d, whose entries along the diagonal are all the eigenvalues of a, is invertible, and we can compute a inverse simply by using the formula a inverse is equal to p d inverse times p inverse. And just as before, we can compute negative powers for a by the exact same formula. And again, we can define a raised to the 0 power because we can define d raised to the 0 power as the identity matrix. So we get p d to the 0 p inverse is p I p inverse is p p inverse, and of course that is the identity. Now, a quick word of caution. Not all invertible matrices are diagonalizable. This is a common mistake. For example, the upper triangular matrix with columns 2, 0, and 1, 2, we can see very easily is row equivalent to the identity matrix. So of course it is invertible, and we've already seen that this matrix has a single eigenvalue lambda equals 2 with algebraic multiplicity 2. However, the matrix A minus 2i, which has a single non-zero entry in the top right-hand corner, is a matrix of rank 1. The rank nullity theorem tells us that the geometric multiplicity of this eigenvalue 2 is 2 minus 1, and that's just 1, which is strictly smaller than the algebraic multiplicity of 2. Let's do an example. We've seen that the eigenvalues for this matrix are 1, 2, and 3. Because we have distinct eigenvalues, we know that this matrix is in fact diagonalizable. And we saw last time. So of course, if we wanted to compute powers of our matrix A, all we need to do is compute powers of our matrix D. Of course, if you wanted to compute A inverse, you could simply take this formula and replace the m by minus 1. And if you ask Sage to compute this for you, you'll see that you get the matrix 1, 0, 0, minus 1 half, 1 half, 0, and 0, minus 1/3, 1/3. And that's about it for powers of a matrix.